All right, so we will work through a sample calculation for the nail lab. The data we're going to start with is as follows. So we're going to assume that the iron nails that we start with and these will just measure directly on the scale, will be 5.31 grams. The CuCl2 solid will have a mass of 3.61 grams. All right, so I'm going to write the balanced equation. We'll talk about where we're going to plug things in. So we have our iron. Iron is Fe. That's the nails. And then the copper chloride, I'm going to write it a little bit differently, and this is explained in the lab. We haven't seen a formula that looks like this yet, and I'll explain what it is here in a moment. So we've got CuCl2, you put a dot and then 2H2O. So the copper chloride that we're using is what's called a hydrated compound. So some ionic solids absorb water from the air. They stay solid and the water molecules are incorporated into the crystal structure of the solid. And this form of copper 2 chloride happens to pull in 2 water molecules for every 1 formula unit of CuCl2. So when we measure the mass here, we're not just measuring CuCl2. We're also measuring some incorporated water molecules. It doesn't affect the reaction, but what it does do is add mass to our sample. So we'll have to account for that in our mole conversion step. Okay. So those are going to react. And we're going to be forming copper, solid copper, just not in a compound, so Cu, plus iron chloride that's aqueous. And then the 2 water molecules that were incorporated in the solid end up kind of being, I guess, released from the compound, and the whole solution is happening in water. So those 2 water molecules end up out in the solution. I'm running out of space. And we don't really care about measuring either of the last 2 components. What we really care about is how much copper we make. So we're going to do the calculations here knowing that that's not something that I'm going to be so concerned with going forward. So let me try to fix this a little bit. Give myself just a little more room. All right, so we're going to do BCA charts. So we'll make a line for B, C, and A. And one thing to note here, it is balanced as is. So there is an assumed 1 here, here, and here. So we don't need to use any real mole ratios in the BCA chart. Okay, so the 5.31 grams is the iron, the nails. The hydrated copper chloride is the 3.61 grams. And of course, we don't have anything over here to start. So our starting mass would just be these 2 numbers added up. I'm going to jot that down up here. Start mass is 5.31 plus 3.61. That is 8.92 grams. And we know that our ending mass should also total up to 8.92 grams if we've done things correctly. Okay, so our next step would be to get into moles, because the mole values are how we're going to characterize the change line, right? So I'm going to take and just go ahead and give you straight away the molar masses for these. So iron is just pure iron from the periodic table. It's 55.85 grams per mole. The molar mass of the hydrated copper chloride, you add up copper, 2 chloride, and then you also add in 4 hydrogen and 2 oxygen because we have that incorporated water. So that molar mass, if you check it, is 170.49 grams per mole. Copper is just pure copper from the periodic table. It's 63.55 grams per mole. FeCl2 is 126.75 grams per mole. And water, 18.02 grams per mole. So my next step would be to convert grams to moles for the iron and the hydrated copper 2 chloride. So I'll do that down below here. 5.31 grams of copper. My conversion factor wants to cancel grams and end up in moles. And I use the molar mass to set up my conversion factor. It's 55.85 grams in 1 mole. So 55.85 grams is on the bottom, 1 mole is on the top. So let's divide that out and see what we get. It's going to be 5.31 times 1, which is just 5.31, divided by 55.85. And we get 0.9507 and then lots of additional digits. I want to keep 3 digits, so I'm going to report it as 0.0951 moles. We want to do the same for CuCl2. Using the same thought process, I need to take the gram amount and divide by the molar mass. So I'm not going to write that out like I did down here. I'm just going to go ahead and type it into my calculator. So 3.61 grams is the sample mass. I want to divide it by this fairly large molar mass. And again, I want to keep 3 digits, so I'm going to record it as 0.0212. I'm going to round up because of that 7. And of course, these are all 0 moles to start. All right, so now I can start to think about what's going to happen on the change line. The lab tells you that the CuCl2 is going to be used up. There will be iron nail left. You don't dissolve the entire iron nail in the solution. So I already know that this is the mole amount that's going to go to 0. At least I'm going to assume it goes to 0. It happens in a 1-to-1 ratio. So if I react 0.0212 moles of the copper chloride dihydrate, that same number of moles is going to react for the iron. Oops, 0.212 moles. Over here, the amount that's going to form coefficients of 1 will be adding 0.0212 moles. Same for the iron chloride, although we're not going to measure it, we can figure it out. And then the water that gets liberated, again, it's just going to mix in with the other water from the solution. That does have a coefficient of 2. So that is going to form 0.0 double 212 is going to be 414 moles. All right, so we can take a look at what we have. So if I subtract 0.951 minus the amount that reacts, 0.0212, I think I punched that in wrong. Let me try that again. 0.0951 minus 0.0212. We have 0.0739 moles of iron left. This is going to go to 0, reacts completely, and then these are just going to be the amount we ended up with once we form the products. They started at 0, and then they added the amount based on the mole ratio. All right, so now we need to convert back from moles to grams, because that's how we're going to measure our end product. And basically what the BCA chart does is it makes a prediction for what we expect in the lab, and then we're going to be able to compare it to what actually happens. So the two key measurements, the ones I'm really focusing on after the lab, will be the iron amount that's left and the amount of copper that's produced. We're not actually even going to take the time to try to measure the other two products. All right, so if I have 0.0739 moles of iron left in my nails, and I want to convert that to grams, I want grams to be my ending unit. I want moles to cancel. And here, that is how we think of the molar mass, as 55.85 grams in 1 mole. So moles will cancel. So here, we're doing the opposite, right? We're taking the mole amount, multiplying by the molar mass to get the grams of iron. And this would be how much iron we think is left after the reaction happens in grams. So 0.0739 times 55.85 is, we'll call it 4.13 grams. So we started with over 5 grams of iron. Through the course of the reaction, some of it gets reacted away, and we end up closer to 4 grams in the end. This will be 0 grams left, we're assuming. And then we want to do the same calculation for copper. We have the mole amount. We just multiply by the molar mass. So this was for iron specifically. I want to multiply by the grams per mole for each substance. So I'm not going to write out the full conversion factor, but we'll do it on the calculator. The mole amount, 0.0212, times the molar mass. Let's call it 1.35 grams. And that's something that you can measure after the lab. You're going to rinse and decant the copper. You're going to dry it to evaporate the water. That's going to be one of our key measurements in the end. All right, so the FeCl2 and the 2H2O, again, I'm not really concerned about measuring them. The FeCl2 is going to be dissolved in water. We would have to actually evaporate the water to get the solid, and the water is just mixed in with the water. You can't really separate out those water molecules from the ones that were already there. So I'm not even going to punch it in the calculator, but to figure out those values, just to check my BCA chart, I'm just multiplying the mole amount times the molar mass. That comes out to be 2.69 grams of iron chloride, and that would be dissolved in the water that we're decanting. And the water amount, this times the molar mass, is actually a pretty small number. It's we're going to call it 0.75 grams. So I'm going to just leave it at 2 decimal places since my other gram amounts were the same. So our final check on a BCA chart is to check for conservation of mass. We started with this many grams of iron and copper chloride. We would want to add these up and see how it compares. That's our total leftover mass, except, I forgot, we've got some iron nail left over here that would be included in that total. So let's do that. Try to get it out of the way here. Okay, so 4.13 plus, this was just a 0 here, 1.35 plus 2.69 plus 0.75 equals 8.92 grams. That is exactly what we started with. So we have very high confidence that we've done our BCA chart correctly. Now, in the video, she actually did measure her final iron amount. She measured it to be 4.20 grams. Experimentally, we're not going to usually get exactly what we expect. She's a little bit higher in grams than she expected based on these two starting amounts. What we'll do is calculate a percent error there. This is going to be a pretty small percent error. It's only 0.07 of a gram away from what we expect. For her copper produced, she found 1.33 grams. Again, very, very close to the expected amount from the investigation. I hope you guys get results that are that good. For this, we calculate what's called a percent yield, which is how much did you make compared to how much you expected. 100% yield is what you want. 100% yield would be you get exactly what you expected. This is going to be a little bit less than 100% yield because she didn't quite make as much as was expected. And we'll talk about those calculations when we do the post-lab. All right, so there's a lot there. We're going to do the same calculations with the real data. We've run through it once. Hopefully that'll help you guys get ready for the lab. Let me hit stop on my screen recording.